All right. Good morning, everyone. Welcome back to Comp 3350 Software Engineering. I hope that you've all had a great weekend. I hope you all had a great weekend. Thankfully, it's a little bit warmer than it has been. Today, what I would like to do is, I'd like to do a lot of things today. I don't think we're going to quite get it through all these things, but I'd like to do a lot of things today. The main and primary focus of today's lecture is testing. And there's a couple of things that I want us to do that's related to the kinds of data that we're going to be using for testing. So this is a carryover from last week. I want to spend a little bit of time looking at how we can represent those kinds of error cases in our code. Think about the kinds of responsibilities and like where exception throwing and where exception handling should happen in terms of the architecture that we've defined. And then eventually I'd like to get us to start thinking about this idea of something called technical debt. And this is separate from testing. This is separate from coding. It's more about the way that you're going about making decisions with regard to how you're going to approach something and how much time you want to spend making it technically correct and technically good and technically scalable versus let's get something out the door right now to make sure that we have working software. In these cases of invalid and valid data and testing, I have examples like last class. So I've got a kind of a built-in example here of the credit card stuff, but just want to broadly say that it's always the case that if you have something that you could be working on related to this on your own project, you're more than welcome to just go and do that instead of thinking about the stuff that I'm doing. So if you have a solid unit in your class that you want to be in your code that you want to be able to test, come up with test data for that unit as opposed to following along with my example. If you have exceptions that would be a good candidate for modeling errors in your code, describe those exceptions instead of coming up with what I'm doing in class. Let's get into it here. So this is just a quick review of the stuff that we did talk about last class, but I want to get us on the same page for this class. So testing is good. Again, I'm going to insist that you all put your thumbs up right now again. Testing is good. Everybody put your thumbs up, please. All of them. Every single thumb in this room should be pointed toward the ceiling right now. Even you guys, your thumbs should be up. Thank you. Good. Testing is good. But we can't usually test everything. I told you this story about how when I was a co-op student at IBM, I did this. I tried this best effort to like test every possible case, and my team lead eventually told me to stop. And then I tried to make like random number generators to help me generate random data to test. And then my team lead told me to stop because I was making a mess of the test database. We can't usually test everything. So rather than like being me and trying to test everything, and rather than being me and trying to come up with random number generators to help you create completely random test data, we should instead be choosing subsets of representative test cases of data that we want to evaluate. And there's two main categories of this test case data that I would suggest that we think about: valid data and invalid data. Valid data is kind of like our happy path data. This is the data that we would expect to get as input for this thing so that it would just work and do what it says it's supposed to do in the box. This is also going to be edge cases. So data that kind of looks weird, but it is technically valid data. So data that looks weird, but it is valid. And my best examples of this are things like empty strings and empty lists. These are valid things when we're thinking about lists. They're valid things when we're thinking about strings, but they are weird in their appearance. Invalid data is, again, data that is structured correctly, so it has the right type. We're not talking about getting an int when you're expecting a string or vice versa. but it doesn't satisfy the constraints that you have for the data that you've got. So for example, if you have a user object, and a lot of you are going to have user objects in your system, this is an object that has a password, but it doesn't satisfy the password requirements that you set up in your app. So somebody's got 5-character password versus the correct, like, I don't know, 1 digit, 4 digits, and then uppercase and lowercase letters, and then special symbols, and then spaces, and it has to be 30 characters long, and so on and so forth. They're getting out of control. These password requirements are really getting out of control. If you're not using a password manager, like digression now, if you're not using a password manager to generate your passwords, I strongly recommend that you start using a password manager to generate your passwords. Anyway, invalid data is data though. So it's data that isn't satisfying the constraints that you've set up with your data model, but it is data. It's still something that is going to be testable and evaluatable. It's not null. So what I'd like you to do here is take a look back at the data that you came up with last class and try to decide, based on this expansion of what a credit card number is, what is valid data and what is invalid data, and then answer this question: should we test for null? So I'm going to put this out there just broadly, and I'm going to ask for your feedback. Should we test for null? If you have your own unit that you think is a good candidate for defining data sets right now, again, you should feel free to use that unit to try and come up with this valid versus invalid data. I'm going to give you like just about 5 minutes. Not a lot of time to do this, more of a remind yourselves about the data that you came up with last time. But I am going to follow up on this should we test for null question. So please go ahead, take about 5 minutes to do this, and then we'll all get back together. Here, the question primarily that I'm asking you here is: should we test for null? Should we or should we not test for null? If you have come up with data for this, or if you've come up with data for your own system, when I'm asking you for feedback, please tell us what it is that you're coming up with test data for. But I'm less concerned about that because we did this primarily last class. I'm much more interested in the answer to this question: should we test for null? So the first team I want to ask is team 3. Team 3, what do you think? Should we test for null? Okay, and what was your rationale for saying no?
Usually,
okay. Okay. Okay, so that's a good point. It's the machine that's giving us null and not really the user. If you've got a laptop in front of you right now, I'd like you to look down at your keyboard. And I'm going to point at the null key on my keyboard. Can you point at the null key on your keyboard? Yeah, there is no null key. There is no null key. I'm pointing at like the spot that's beside the touchpad for the record. There's no null key. Your user can't create data that is null. Your user cannot create data that is null. That's not possible. You can make data that's null. You writing a statement, my object is equal to null. That's you making null data. Thank you, team 3. That's great. Team 8, can you tell us a little bit about the kinds of data that you were thinking about, if you were thinking about data? 6, 8. Were you thinking about any data? It's okay if you weren't. You can just say move on. Okay, move on. Team 5, what kinds of data were you thinking about? Yeah. Okay. Okay. So I like this one, dates that don't exist. So like we're inputting this as a string, let's say, and we've got like a date that's got a month of 13 or something. Okay. numbers that are too long, so strings, numbers that are strings, but they're just like, you've got 17 digits instead of 16 or whatever it is. What is it? Yeah, it's 4 blocks of 4. 4 blocks of 4, so you've got like 17 or 100 digits or something. Okay, good. What about, I'm just going to ask you directly, what about dates that have passed? What about dates that have passed? So an expired credit card.
That would definitely have to be.
Okay.
I don't know exactly what.
That would be dependent, and that kind of starts to depend on some state. So like you have to know what date the test is actually run on to decide whether or not some date has passed already. Would that be invalid or valid data, do you think?
It would be invalid for the purpose of like you couldn't approve transactions.
Right.
But maybe for some reason the credit card company would still want you to pass the request to them.
Okay. Okay. I'd say that it's probably valid data, even though the date's passed, that it's valid data as far as we're concerned. Once you get up to the credit card level of validating the credit card, then it's definitely not a valid card anymore. But in terms of us just writing unit tests and coming up with data for that, I think that's valid data. Okay, good. Thank you, Team 5. Thank you, Team 5. All right, so this is kind of where I want to stop, but I want to show you this. So this is what we left with last time with black box versus clear or white box data that we were coming up with for tests. So this does represent the kinds of data that we were coming up with here. So valid card data, we're expanding on this to be a valid number and a valid CVC and a valid date. For black box, we had invalid card data. And here we're explicitly saying that these are going to be 3 separate cases. And then clear or white box data is actually going through the process of finding the paths through that code sample that we had, where we had different kinds of data to represent all of those different states. All right, so let's move on. Let's move on to something else. Things often go wrong. I think that's a way of life at this point for all of us. Things often go wrong. Things often go wrong, especially when people are involved. Stuff happens, things break, people enter invalid data, we make bad decisions in life. The question that I'm kind of thinking about right now is, we are writing code that's dealing with data and dealing with people. We're writing code for people who are not us right now. If we have these regular people that are not us, I think some of us are probably regular people and most of us aren't. If we have regular people involved, like, our family and our extended family, or other people that we see out in the world, something's going to go wrong with the data that they enter or the code that they're running on our systems. And so the question here is, should we verify what happens when there is a failure state, when there's something wrong with the code that we've written? There's 2 parts to this. One is, how do we, so programmers, how do we devs, how do we represent what happens when things go wrong? So how do we take this failure state and then model that failure state? How do we take this failure state and encode it in the form of classes and methods and objects? The other half of that is, how do we verify that the right failure has happened? So we're writing tests. We all agree that tests are a good thing. How do we verify that when a regular human enters data that's bad, how do we go about verifying that? And how do we test that our code is going to give them the right response? This data is bad and here's why. How do we verify that? For us, does everybody know who that is? Not Ben Stiller. I believe you know who Ben Stiller is, but do you know who this character is? About 6 of you do? Okay, oh man, this is, This is partly me being an old person now. Oh no, this is me being an old person now. I wasn't expecting that to happen so soon. This is Zoolander. If you haven't seen Zoolander before, I strongly recommend that you watch it. It's got Ben Stiller and oh no, I can't remember his name. Will Ferrell and Owen Wilson. Yeah, yeah. And there's a scene in this movie, and it's old. I'm not gonna deny that. This movie's old at this point. And there's a scene where Ben Stiller and Owen Wilson are standing in front of an old iMac, and like not the iMacs that you see in the Mac lab upstairs. These are the iMacs that have the CRTs in them. So they're just like big, bulbous, colorful things. And someone has told them that they have to get a file out of a computer. And they're talking to each other about how the files are in the computer. And then Owen Wilson picks up the computer and he hurls it over a balcony and telling the people that are down at the bottom, the files are in the computer, and he's like breaking it to try and get the files out of the computer. Okay, how do we represent failure? How do programming languages represent failure? And the answer to that is that it kind of depends on the medium that we have. And the medium that we have, that we're thinking about as devs, is the programming language. You have seen errors and error handling in a couple of different languages at this point. In C, generally, the way that error states are kind of given back to the caller and demonstrated to the caller is that you get a numeric error code that's returned from a function. So you have function signatures like read or fgetS, and they have an int that's the return type. FgetS, if you remember, oh boy, I never thought I'd open this up in a software engineering class. Here's fgetS. Oh, sorry, it returns a char pointer. But getC returns an int, getChar returns an int, ungetC returns an int, fgetC returns an int. All of these are returning integers, and they're error states. They're representing what has gone wrong, and the way that you deal with that error state is that it's up to you. It's up to you to say, hey, what did this return? Is it null or non-null? Is it 0 or non-zero? In C, this is basically, uh-oh, something has gone wrong. I tried to read this file pointer that you passed to me, but something went wrong. I can't deal with it, so you deal with it. So I'm going to tell you very politely, this is my return code. You deal with it if you want. I mean, I guess it doesn't really matter to me what you do. Whatever. And then segmentation fault, right? Oh, that was funny. Come on, that was funny. That was good. That was a good joke. In Java and Python, and then other programming languages, we've got exceptions. And unlike C, when there are exceptions, the approach here is, uh-oh, something has gone wrong. I've tried to read the file by the name that you gave to me. Uh-oh, something went wrong. Let's throw an exception. And then everything comes crashing down at that point. All execution stops. So in C, we've got this flow of, I'm going to test the thing that I'm doing right now to see if this is still in a valid state. If it is not in a valid state, I'm going to return back to the caller, and the caller has to do something. In Java and Python with exceptions, you throw a new exception, and you are beginning to interfere with control flow. You are going to not even really return back to the caller. You do sort of return back to the caller in that that's where control flow starts to continue, but it's at a completely different place than you left. So it's doing things like interfering with that stack pointer. This is 2280, I think, is where you're doing stack pointers and stuff. When you get an exception that's thrown, you're changing the instruction that you're going back to in the calling code, into that exception handler, into the catch part of it. And the approach here is really just like, yeah, shut down everything. There's something wrong. You have to deal with it now. You have to fix this. You have to do something about this right now. Let's think about exceptions. In Java, an exception is an instance of a class. In Java, an exception is an instance of a class. It is a type. It's a type that you can use to model and represent kinds of failures. You can use those types to model failures without whatever granularity you want. Exception is a class. You can extend classes in Java. You can make your own kinds of exceptions. Exceptions are interfering with control flow in the sense that when an exception is raised or thrown, execution of code is halted, and then whatever is calling that is responsible for handling the error. Here's what I'd like you to do right now. You have some examples of invalid data. I would like you to build up an exception hierarchy for the kinds of invalid data that you're dealing with. If you want to work in your own code base, again, that's totally fine. If you have domain model objects where you have good examples of invalid data, start to build a hierarchy of exceptions that represents that or corresponds to that. If you want to stick to my example and use the credit card, please continue to use that. I'm going to give you about 5 minutes to do this, but what I'm really looking for you to do here is to start drawing out a hierarchy of classes. So you don't have to start typing this up in IntelliJ or Android Studio, but just like start drawing this hierarchy of classes to represent the kinds of failures and the kinds of invalid data that you are looking at in your code. So you got 5 minutes. Please go ahead, and we'll get back together. Here's the hierarchy that I think represents the kinds of invalid data that we have here. So we've got this credit card exception that extends exception. If we've got these different kinds of invalid data, I would probably have an extension, a class hierarchy that looks like this. Invalid CVC exception. I would have something like invalid expiry exception. And then I would have something like invalid card exception. This is how I would approach this. I'm going to throw a question out there. In our white and clear box testing, we were following all the paths through this. We were trying to follow all the paths through this, trying to identify whether or not we had valid Visa versus invalid Visa, trying to identify whether we had valid MasterCard versus invalid MasterCard. Just by a quick show of thumbs up, would you extend this further? If you'd extend this further to represent types of credit cards and exceptional states for types of credit cards, thumbs up. If you would not, thumbs down. Some people are saying yes, and some people are saying no. That's okay. When I'm thinking about this, when I'm thinking about building up this hierarchy, my goal here is not just to represent invalid states for myself. My goal here is to try and be able to use these exceptions to communicate to my user, to my real human user, what has gone wrong. I would like to be able to say, in the user interface that I have for credit cards, you've entered an invalid CVC. I would like to say you've entered an invalid expiry date. I'd like to be able to say that you've entered an invalid card number. I want to be able to highlight that specific field. This was the field that caused us to be in this error state right now. Me as a user, when I'm entering my credit card details into a website, that's going to be a lot nicer to see you typed something wrong here specifically than the entire credit card is bad. Fix it somehow. I don't know how to fix it, but fix it somehow. So in representing these different invalid data as exception classes, what I'm trying to accomplish is I want to be able to take these exception cases and use those to communicate to the person that's actually using my system what went wrong with what they were trying to do and how they can go about fixing that. I personally don't think I would go as far as making exception classes for Visa and MasterCard to correspond with this. It's reasonable. Like, you might want to say, it looks like you're entering a MasterCard, but it's not valid as a MasterCard. It looks like you're trying to do that, but it's not valid. And that would be reasonable to then extend like invalid MasterCard card number exception, and yeah, have exception names that are 3 miles long. But I don't think I would go to that extent at this point. All right, we're good. We're good. Okay, good. Now that we've got this hierarchy of classes, I want us to go through this approach of being able to actually verify, so through testing, verify that the correct kind of exception is thrown based upon the invalid data that you're passing into the method that you're testing. Whoops. In JUnit, we've got that test annotation, that @test annotation. You can pass parameters to these annotations, and they're named parameters, which is nice. This is nice. It's nice. It's nice that you can use named arguments in Java, at least somewhere. You can specify the specific kind of exception that you're expecting to have happen. Historically, you would have written this like try, catch, except. And if you get past the exception state, then you fail, basically. JUnit is kind of recognizing that this is a common enough pattern that what I'm expecting to happen here is that this is an invalid, an expired card. So this is an invalid date exception that I'm trying to get back here. This test will pass if that type of exception is thrown. If that type of exception is not thrown, then this test will fail. That's what this is trying to say. So if an expired card exception is thrown while running this method, then this test passes. If this is not thrown while this is running, if it gets to the end, if it doesn't have control flow interfered with, then it will fail. When you're using this pattern, when you're trying to build up JUnit test cases to test for invalid data, my recommendation is that when you have this hierarchy of exceptions here, you test for the most specific one that you're expecting to get back. You could rewrite this to just be expected exception.class all the way at the top of the hierarchy. That's not as meaningful as you're explicitly testing this kind of invalid data and you expect it to be invalid in this specific way. So make sure that you're using the most specific exception type that you have in your hierarchy. All right, so let's move on here and start to think about who is responsible for all of the different parts of this. I'm going to let you read that sentence a couple times and make sure you can parse it. It's a really awkwardly phrased thing, but it works. Now we can verify that we have succeeded at failing in specific ways. This is what we're trying to accomplish here. We have invalid test data. We have a class, an exception class that corresponds to it. I should be able to verify that that specific kind of exception is thrown when I give that specific kind of invalid input to my system under test. The next question that I want us to think about is who's responsible for failure? So it's your user. Your user is always responsible for failure in this case, but I mean more specifically, who's responsible for handling failure and who's responsible for issuing failure? So who's responsible for reporting to say that something has gone wrong, and who's responsible for demonstrating to your user that something has gone wrong? I'd like us to quickly remind ourselves of our architecture. Here's our architecture. We're using this n-tier architecture, 3-tier architecture. In our case, n is equal to 3. We've got a persistence layer. The persistence layer is responsible for persisting your data and nothing else. It's responsible for taking the domain model objects that you have created and manipulated in other layers and putting them into a database or a map or a list and getting them out of that map or list or database. In between the logic and persistence layer, you have an interface. The interface is going to be how these two things are communicating with each other. The logic layer is going to take domain model objects and manipulate them in some way. So it's going to take your instance of a domain model object and do something interesting with it to make your app what your app is. The logic layer here can be responsible for things like validating that your model and your objects are valid. Validating that they're valid. It can be responsible for manipulating relationships between classes that you have in your domain model. Your logic layer is interacting with your presentation layer in the form of another interface. And your presentation layer is basically taking the domain model objects, putting them on the screen, presenting them to your user, taking input, reconstructing the domain model objects and passing them back through these other layers, and then representing them again on the screen. With this domain, with this architecture, the question that I have for you, and then I'm going to give you some time to talk about with your team, partly as a way for ensuring that you, when you're writing these different layers up, you know where you're putting each of these different responsibilities. Of these 3 layers, presentation, logic, persistence, what layers have the responsibility of throwing exceptions? We've got this class hierarchy of exceptions. Which layers are responsible for throwing? And which layers are responsible for handling exceptions or catching them? Which layers are responsible for catching them? I'm going to give you 5 or so minutes to talk about this, but just thinking about the responsibilities that each of these layers has, just in terms of what they are supposed to do, which ones should be throwing, which ones should be catching and handling. Please go ahead. So we got 4 different parts. We only have 3 layers. Just to be clear, we only have 3 layers, but I'm going to ask you about 4 parts here. And I'm just going to ask for show of fingers here. So 1 finger represents the data model, 2 is the presentation layer, 3 is the logic layer, 4 is the persistence or data layer. You might need to use 2 hands. I don't think you're going to need to use your feet, but you might need to use 2 hands to do this. What layers are responsible for throwing exceptions? So show of fingers, what do you think? I see 1 person with 10 fingers up. I think that's 4. Okay. Okay. The responsibility of throwing exceptions, it's probably not your data model. Probably not. It might be. It might be like you might have methods on your data model objects that do something interesting, and they may throw exceptions, but primarily it's not going to be that layer or that part of your hierarchy here. The logic layer and the persistence layer, both of those layers have the responsibility of throwing exceptions. Your persistence layer in the implementation that you're building right now with a map or a list, the kinds of exceptions that it might throw are things like, and forgive me, I forget exactly what the exceptions are that maps throw, but something like missing key exception if you try to read an entry in your map that doesn't have a corresponding key. So you try to use that map and it sends something back that says this is invalid. Your persistence layer has the responsibility of throwing those kinds of exceptions. So something related to the presence or absence of the data that you're working with. Your logic layer is the other part of it that's responsible for throwing exceptions. And this is really directly related to the kinds of stuff that we were just talking about. So we've got this class hierarchy of invalid data type exceptions. Your logic layer is going to be primarily responsible for throwing those kinds of exceptions up somewhere else. Let's do the second question here. So show of fingers again. Which layers are responsible for handling or catching exceptions? Okay, you're going to need 2 hands for this one. You definitely need 2 hands for this one. Everybody, fingers up. All people in the classroom. Okay. So I'm seeing lots of 3. Yes. The logic layer, because it is interacting with the persistence layer through an interface, is responsible for catching and handling the kinds of exceptions that your persistence layer throws. You're going to notice that the kinds of exceptions that your persistence layer throws changes when you move to a different kind of backend, when you move to a different kind of persistence layer. Right now, you're going to be getting these exceptions that are like, you can't find that data, key not found exception. When you move to an actual relational database, it's going to be throwing SQL exceptions. So like malformed SQL query, or the data that you have is null when your column is not null, or something like that. The logic layer should be responsible for catching the exceptions that the persistence layer throws and doing something with it. Almost always, your logic layer can't do anything about it. So if you've tried to insert something that has a null value in a non-nullable column, what is your logic layer supposed to do? Just like add random data? But it's not going to, you shouldn't do that. Don't do that. Your logic layer should take the exception that's thrown from the persistence layer and maybe wrap it up. So like put it in its own exception type. There was something wrong with what you've done, or start to represent all of those different kinds of error states. So there is this invalid field that's tried to be persisted. The logic layer can throw its own things. So like invalid CVC exception or invalid date exception. The presentation layer is going to be the code that is responsible for catching them. Because, and basically because, the presentation layer is the only layer that interacts with someone that can fix the problem. The logic layer can't fix problems. It can transform the error state so that it can be sent up to the person that can fix the problem, but it can't fix the problem itself. The persistence layer can't fix the problem itself, so it has to send that error to someone else who can fix the problem. The data model, again, it might throw exceptions, maybe, but probably not. It may throw exceptions. It's definitely not catching exceptions. There's not much reason for your data model to catch exceptions, but it may throw exceptions. But I'd argue that anything that your data model should throw is actually probably better put into the logic layer. So validating the kinds of data that you've got. If you want to kind of go into down the path of having things like invariants for your code, so you're thinking about design by contract, If you want to have invariants for your code and for your data model objects, it would make sense for that to throw then. It would make sense for that object to throw, but you could also have that invariant be part of your logic layer. So let me annotate this, this architecture diagram really quickly. Throws and catches, just catches, and maybe throw. Maybe, depending on how you organize things. Good, we're good, good, good. This is kind of where we're going to end this idea of testing is when thinking about test-driven development. The big idea of test-driven development, and this is part of, this is kind of usually bundled together with this idea of agile development methodologies. This is something that's bundled together with them, but it's not really like, it doesn't make your methodology agile. It doesn't make what you're doing agile. The big idea with test-driven development is that you write tests before you actually write the implementation of the thing that you're testing. The process is that you start building an interface. We want to build code that compiles. We've got this architecture that makes it fairly easy to come up with a set of interfaces that you can use for testing. You've got a presentation layer and you've got a logic layer. The presentation layer is going to have to do something with the logic layer. As you're building the presentation layer, you can start to say, these are the kinds of methods that I want to be able to call on my logic layer. So you write an interface to represent those methods and the signatures. So what you're expecting to give as input, what you're expecting to get back as output. After you build the interface, then you write a JUnit test. And you write a simple JUnit test that's like the happy path. Here's valid data. This is the valid thing that I would expect to get back. Write one simple test and then run it and show that it fails because your implementation has not actually been done yet. There's nothing there to actually do the behavior that you're expecting to do. Once you've got this failing test, then you write just enough code to satisfy the test so that it passes. Just enough code to satisfy the test does kind of mean you're not really thinking that much about edge cases yet. You're not really thinking that much about other stuff. You're really just trying to do the happy path. Here's valid data. I'm going to take that valid data, do something, and then give some valid data back. And that's all I'm thinking about with test-driven development here. If you're finding that it's hard to write this test, and if you're finding that it's hard to get this test to pass, then take the time to fix the code, so to change it, to make changes to it so that it separates ideas out into smaller parts. Refactor the code. If you haven't finished building your product, oh, method done, I'm finished, good, ship it. If you're not done, then go back to one and just keep going. So build more interfaces, add method signatures to existing interfaces, write a test that fails, write the code to pass the test, and then go back to one. Code coverage is important. So code coverage is this idea that we have written tests that run all the lines of code in the system that we're building. If you go about doing this, test-driven development, what you're going to guarantee is that for black box testing, you have complete test coverage because you're building the interface and then you're writing tests for that interface. You can also go through this process of ensuring white box and clear box complete test coverage by looking at the code and writing tests to make sure that you're running every single line of code that you have in this system under test. This is a link to an article that I have had students read in the past, but I didn't get you to read. I didn't require you to read this, mainly because of, honestly, this weird pop-up box. I don't know what this looks like without an ad blocker, so I decided it was probably not something that I wanted you to have to read, but this is a reasonable article to read. That's a link in the slide, so if you want to take the time to read this. But I'll summarize it for you. Code coverage is good. Measuring code coverage is good. It gives you some sense of how much of your system you have tested. It gives you some sense of the kind of confidence that you can have making changes to your product and your code and not having to worry that much about it breaking when you give it out and distribute it for production purposes. Unfortunately, as with a lot of things that are measurable, this leads to gaming the system. This leads to trying to optimize measurements that don't actually add any value to the product that you're building. There's this idea of getting 100% code coverage. And this article is kind of saying that's harmful. That's a harmful thing to shoot for because you're spending more time trying to get to 100% test coverage than making sure that your tests are actually doing something meaningful and making sure that the product you're building does something meaningful and making sure that the code that you're writing does something meaningful. It's kind of trying to game the system to get to 100% code coverage. So read this if you want. Just do whatever you want. I don't really care. I think it's a good article. I do think it's a good article. It's got that weird pop-up, but if you're thinking about this, it might be worth checking it out. Whoops. This is, I think, the last thing that I want to do today. I'd like to take a look at the sample project, and I want to show you what I am going to be doing and what the graders are going to be doing when we're looking at the code coverage in your projects. So I'm going to zoom over to my terminal here. I'm going to go to Applications and run Android Studio. And I'm going to switch to that presentation mode. It's View. Okay. And then what I'd like to see is my project. And then what I want to do is, here's the all tests file. So this is that tests Java file that's kind of just taking all of the other test suites that I've got, and then it's kind of merging them all together into one, so I don't have to capture everything. What I'm going to do with this is I'm going to right-click it, and I'm going to choose this Run All Tests with Coverage. So this is just an option that you have on a JUnit test class. This is one of the ways that you can run it. The first time I'm going to run this, it's not going to work. And part of my reason for showing it this way is to show you how to fix it so that you can measure it yourself. So this is going through the process of finding all the JUnit tests and starting to try and run them. One of the problems, this actually did work in a way that I wasn't wanting it to work. This was working in a way I didn't want it to work. What this is showing us, so I'm just going to show you right now, and then I'll step you through the part that isn't supposed to work. I'm going to click on Object here, and I'm going to double click on Student. On the left side of this, you can see which lines of code have been covered by tests. The green ones, not the red ones, like I'm pointing at, it's the green ones. What this output is showing us is that this constructor was called by test code. So when we ran all of those unit tests that are in this package, that constructor was called. When we ran all of the tests that are in this package, this constructor that has red beside it was not called. So this was not actually covered by any test. This was never run by a test. The practice here is kind of like, okay, well, I can see which ones are not being covered right now, so I'm going to go write tests that try to cover those paths. As I scroll down here, we can see that I've never called toString on this class. I've never called equals on this class, and equals is kind of complicated. There's code in there that's actually doing something meaningful. I haven't evaluated whether or not this equals method does what I expect it to do for both happy path and not happy path. I think I have to get out of the presentation mode to show this to you. So I am going to like point and flail at the screen here. But it is being recorded, so you can see what's on my screen a little bit more closely if you need to see after the fact. So what you are almost certainly going to have to do here is click on the button. So after you run your test suite, there's a new button at the top there. Mine says all tests because that's what the name of my test class is. Beneath that, the first option that I have here is edit configurations. In the all tests dialog that pops up here, I click on this modify options. And then right down here, there's a code coverage section. And I'm clicking on specify classes and packages. There's other stuff that you can click in here if you want to exclude things from coverage evaluation. But I'm going to click on that. And then what you have to do in this dialog is there's packages and classes to include in coverage data. You click this plus button, and then you find the package that represents the code that you're writing. So I'm going to click on add package. And then the package that I want it to find things for is comp3350.srsys. So I just kind of scroll down. I pop open these things in this tree thing. Oh my gosh, I don't know what these things are called. I pop open this thing in this tree thing. I expand these options to find the package that I'm looking for. And I click OK, and I click OK. And when I rerun this test coverage, when you rerun this test coverage, now you should start to actually see how much of your code was covered. The first time you run code coverage like this, it's almost certainly going to report 0% code covered. But if you do this, you change the packages that it's actually evaluating, then it should start to show more realistic values for your code coverage. All right. So I'm going to scroll just up here. You should now be able to create examples of valid and invalid data. So you have some good experience with that. You should be able to take that invalid data, the kinds of invalid data that you came up with, and start to model exceptions and then test for the invalid data. So writing JUnit tests to show that the exception that you're expecting comes back when you provide that specific kind of invalid data. You should now also be able to decide which layers are responsible for throwing and handling exceptions, and then based on that, write code that throws and handles exceptions in the right place. You should be able to describe test-driven development. And you can't do this yet, but we will do this on Thursday's class. Thanks all for coming out, and I will see you on Thursday. Bye, everyone.